Welcome everyone to Geeks for Geeks. Today we will be solving Codeforces round 745 Division 2 Problem E Train Maintenance. So let me just read through the question. So what it's given is, okay, Kawashiro Nitori is an excellent in engineering. Thus she has been appointed to help maintain trains. Okay, so there are n models of train. Okay, and the tourist department will only have at most one train of each model at any moment. Okay, in the beginning there are no trains. So okay, so initially we don't have any trains. At each of the following m days, one train will be added. So if we visualize it, then from day 1, day 2, day 3 up till day m, is given that one train will be added or one train will be removed, and it is also mentioned that she can have only one train in the department. So for instance, if train there are from one train numbers are from 1 to n, so maybe on day 1, for example, we can say that let's say, and for our example we can consider there are 4 trains and the number of days are 5. Let's consider 6. We can say that on day 1 maybe train number 2 was added, and on day 2 again train number 4 was added, and on day 3 we may say that it's just an example that train number 2 might be removed, and on day 4 again train number 4 might be removed. So this is what information we have as of now by reading halfway through the question. So let's go ahead and read the remaining part. When a train of model I is added at day t, okay, means th day between 1 to n, okay, it works for xi days. Okay, that's interesting. It will work for xi days including the th day. Okay, so the day in which it is added, it will also work on that day also. Then it is in maintenance for yi days. Then it works for xi days again, and so on until it is removed. Okay, this the final part of this paragraph is very important to understand. Let's break it down. So it is given that for instance, on the ith day a particular train is added. Let's say the train A is added on the ith day. So and we also have the information that for train A, after it is added, it will work for xi days. Okay, xa days, sorry, like the train of model A on the ith day, I am saying it on the ith day, the train, if a train of model A is added, then it will work for xa days, and then it will again rest for ya days, and then if it's still present in the department, it will again work for xa days, and again after completing xa days it will also work for ya days, and the process will keep on repeating like that. Okay, and one important thing to keep a note is that on the day it is added, it also works for that day. So like this will be something to keep a note of as we go ahead. Okay, so go ahead and read more. In order to make management easier, Nitori wants you to help her calculate how many trains are in maintenance in each day. Okay, basically the idea is there will be m days. Yeah, in the question it is mentioned there will be m days. So for let's say 1, 2, m days, we need to find out is on each day, on the ith day, how many trains are in maintenance. Okay, in maintenance. Okay, let's just kind of look at the constraints once. Okay, N and M basically from one, they can be from 1 to 2 into 10 to the power 5. Xi and Y, okay, they're also they can be up till 10 to the power 9. And it is mentioned that if OP is 1, then it means that a train of model K is added on that day, or if it is true, then a train of model K is ejected from the department on that day. Okay, let's also read through the last line. It is guaranteed that when a train of model X is added, there is no train of the same model in the department. Okay, it kind of makes our life a bit easier. And when a train of model X is removed, there is such a train in the department. Okay, okay, kind of like the final statement kind of escape helps us in determining that we won't have any corner cases in which maybe we need to add a train and already the train is added, or maybe we need to remove a train and there isn't any train of that kind in the department. Okay, okay, the question seems interesting. Let us kind of first try to analyze it and kind of come up with a basic understanding of the approach of what shall we do. Okay, so the first thing that we are able to see is that for instance, let's say we have 4 trains. Let's consider 5 trains, and let's say up till and M, maybe let's say 7. Okay, now here we are what we're able to see on the first day. Let's say the train 3 is added. 3 is added, and by the way, or let's consider it has x and y value as 2 or 4. Similarly here, let's consider it as 3, 2. Consider like first value represents the x and the second value represents the y. X means it will work for x days, and y means it will be in maintenance after x days, and it will kind of go on repeating like that until the train gets removed. Consider 1, 1, 4. Let us consider 2, 3, 4, 5. Let us consider 1 and 2. So really, if the train 3 is added, so 3 we know it will work for 1 day. So from this example we can see that just for the first day 3 will be in active work mode, then just on the second day it will have to move towards I will just work and maintenance. M represents maintenance, so on the second day it will have to move up till the maintenance. Okay, let's say on the day 2 we added the train 3. Okay, 3 that sorry. Let's see, on the day 2 we added the train number 1. So 1 comes here in maintenance. Sorry, work. 1 will be in work. Then on the third day, again 3, since it spends only 1 day in maintenance, it will again come back, jump up to work set, and 2 will already 1 which is already added will since it has it works for 2 days, it will still remain in the work set. Okay, now let's say on third day we try to eject 3. So if we eject 3, then it will go out. It will no longer be available on the in the work set, and 1 is still available. Okay, so like just by looking at this step, we kind of have an approach in which we will kind of have maintain 2 sets. One will be the work set and one will be the maintenance set. and after each after we move from the ith index to the I plus 1 index, we will kind of keep a track of which elements are kind of getting changed, and kind of swapping the elements in between the sets. But the issue that may arise in such a situation is for keeping the track of which are the elements that will kind of change set or at the ith index, we can have a map, like in the map the first element will be the index, and with the second element we can consider a set to make our lives easier, a set of indices, like the set of trains that will change their value, they will change the set, like basically we have two sets, right? The works one set that has the trains that are working, and the other set that has trains that are in maintenance. So we can have a data structure like this, in which at every indices, as we move through 1 to m, we keep on storing it and keep on flip-flopping it as we cross from one index to other. Well, the issue that may arise in that case is, for instance, here we were able to see that here xi is 1 and y is 1. So means we can see that every alternate day this train kind of changes its set. Like, what if we have a case in which almost all the n trains have xi as 1 and yi is 1. In this case, after every shift, after some, like almost a major portion of the trains will be keep on swapping their sets, and eventually, in the worst case, we may say that in that case we will have a time complexity of around O of n star n, which ain't good for this problem, as in this problem we can see that limits for n and m are to 2 into 10 to the power 5. So like this is the simplest of brute force approach that we can apply, but the brute force apply won't work. We need some kind of optimization and observation. Okay, so let's see what we can do. Okay, so the one thing is to observe that for, let's say, the train a a, for instance, a tray n enters at some index. So from from here up till x amount of time it will work, then again up till y amount of time it will remain in maintenance, again it will work for x, and then again it will come under maintenance, and the process just goes on like so. Let's say it entered the indices I at the ith indices of the m, and for instance let us consider it was inside the department up till the mth index. So what you can see is, you can see that this part and this part are basically the same. So what we can kind of think about is that, so what we here we can see that basically this kind of forms a cycle. Again here we have another cycle, and so far and so forth, there will be cycles, and eventually at the mth index we only care about whether in the mth index we only care about whether it is inside the axis part or the y-th part. Means in a sense that, okay, I will kind of reiterate this part. It's very important to understand this. So for instance, let us take an example to understand it. So let's say indices 1, 2, 3, 4 and 5. Consider 6. and here consider x is equal to 1 and y is equal to 1 for simplicity. So if a train enters here, here it will remain in work for the first index, then it will go in maintenance, again work, again maintenance, again work, again maintenance. So what we are here able to see is after a complete cycle, it kind of again returns to like after x plus y, like after x plus y indices get completed, it again returns to the initial state, which is it again starts from x and y. So and eventually if we only want to know the state of the train at 6th position, we we can kind of just divide this length and kind of check out what will be the only thing that matters is whether the train is in active mode or in maintenance mode, which can be obtained by the simple observation is that you can find the the difference of the distance mod of x plus y. Now if for this example here we are able to see that comes 5% to which is 1. So we are from here we can easily conclude that at position 6 it will be in under the maintenance row. If it would have been let's consider 5, we consider 5% x plus y which is plus 1, so you can see it comes 0. So we are easily able to say that at index 5 since it's 0 and 0 is less than x value, so it is under work condition. So one important observation here is that if we just know the index at which a particular train is added, then using that at any index we are able to find what may be the final state of the train, whether it will be in active mode or whether it will be in maintenance mode. Okay, this is a very important observation. Okay, now since our basic idea that kind of got developed of the earlier observation is that if we kind of divide the segment of the starting index to up till the index we want to calculate, so we just need to divide this segment by x plus y and kind of take the modulo, and in that case we will be able to tell is whether the particular train is in a working state or in maintenance state. Okay, now let us observe this x plus y. So here we are able to see that x for a particular train xi and y can be as large as 10 to the power 9. So first thing is we have m indices. Okay, fair enough, we have m indices. So out of an this if we observe one thing, if I say that for a particular train the value of x plus y is more than root m. Okay, so if for a particular index the value of x plus y is more than root m, then we can then the segment, for instance let us consider entire segment from 1 to m. So the entire segment can eventually be divided into m by root m, which is equal to again root m. So the entire segment from it can be divided into root m parts. Okay, it kind of makes sense. Okay, so what I'm saying is if we can divide the remaining segments in root m times, then For instance, if at the ith index a train A is added, then one more thing to see is we need to find a number of trains in maintenance. So to find that, we can do one thing is we can find the total number of trains that are available in the department minus the total number of trains that are in active state. In active state. In active state. Like this will eventually give us our answer. Okay. So what I can do is, if this condition satisfies, then uh, the moment a train I is added, a train A is added in the ith index. So from I plus x value, so up till I to from I can kind of keep a count and increase this count by 1. I will just increase this, means one count by 1, and at I plus x, and I plus x, I kind of know that it will now go into maintenance, and I can decrease this count by 1, and I can kind of do it for all the root m segments that I will be getting, since I will at max get root m segments since x plus y is greater than m. So for instance, I have done here from I, and then in the next iteration I can have I plus x plus y, and again in the next iteration I will again have plus x plus y, and so far and so forth, and this will go, and at max this will cost me root m times. Doing this will kind of help me keep on track of what are the portions between 1 to m in which the train A will be in active state. Okay. Now the second condition is, what if x plus y is less than root m? Then there may be a lot of segments in that case. So one key observation that is very beneficial, and it kind of comes from the idea of square root decomposition. You can refer to other videos of Geeks for Geeks on square root decomposition for better understanding of the topic. So one great idea of one good idea of kind of solving it through is that since x plus y is less than root m, so we can already have an array of root m. So like what I'm saying is, I can have an array, for instance, for like from 1 up till I'm going to root m, and for 1 it will have 1 element, for 2 it will have 2 elements, and so far and so forth. For root m it will have root m indices. There will be other indices also, since we will be considering a 2D array, but they won't be much of use for us. Okay, and here so far, and for 3 there will be 3 indices. So what you can do is, since x plus y is less than root m, then we can since x plus y is less than root m, so what we can see is this. For instance, let's consider that x plus y is equal to 3, and of this 3, x equals to 1 and y equals to 2. So if so only the trains that are in this block will be inactive, and the remaining 2 blocks will be in maintenance, and we only care about the number of trains that are present in the active block. So what you can do is, for every start indices that I get, I can just keep a modulo of it with x plus y, and whatever, for instance, my start index is, let's say, I, so I can keep a modulo of it, and whatever of this tree value it comes, I can kind of keep that value as a count in one of them. This will indeed help me, because I won't need to have more than have the issue of go, like in the earlier case I had the issue of if I went ahead directly, then I would have to go more than root m times. But again, by this analogy, the thing, like for x plus or less than root m, we do not have to go more than root m times. Okay. I will just if like and now I will be kind of going through each and step by step through the code, so that you can have a better understanding. Okay, this is the code. Don't worry, it's quite it's simple. We will go through each and every step carefully. Okay, so basically first we are taking in n and m, and then we have like xn and yfn are the two are kind of x and y are the same, that represents the working time and the maintenance time for the ith train from 1 to n. Then we have a vector called particular. This particular vector kinds of tells us, like this particular vector that I have taken will kind of keep a count of this case, which is case number 1, in like for all the cases in which the added train had a x plus y value more than root m, in which we are kind of directly doing a brute force over root m segments, kind of keep a count of which are active and which are not. So this particular relay is for that case. And the second 2D vector, which is exact. By the way, for since we are considering only root m, so I have taken int magic as square root of m plus 1. In this particular exact array will be helpful for us in considering the second case. Now let's see how. And then we have vector, and this vector memo kind of memo day kind of keeps a track of this starting day in which the ith train entered the department. Okay, so we have a for loop for day, in which day is going from 1 to m. Okay, so this is it is so the first thing is it's kind of doing similar to the stuff related to prefix sum. Like for instance, there is a range 1 2 3 4 5, and you know that the value of like for instance a particular value is present up from 2 up till the point 4, so what you do is you basically do a plus 1 here and you do a minus 1 here, and eventually when you took a cumulative prefix sum, once it consider here 0, then it was 0, it becomes 1 1 1 and again 0, and this one kind of says that the particular element, the element e, was present from 2 to 4. A similar thing is kind of happening here also. Okay, then we take the input op and k. So for change, like there are two things said, one is addition and one is subtraction. So like for change, like in addition, Like for instance, if we take this analogy only, in addition we do a +1, and when we need to remove we do a -1. A similar thing is happening. Like change here represents 1 if something is added, or -1 if something a train needs to be removed. Okay, now if OP is equal to 1, then it's obvious, like we kind of keep a track of that it is this day in which a train got entered. Okay, and active here represents the total number of trains that are available in a department. Okay, now, okay, so there are two cases. First case is if x plus y is less than the magic. Magic means the square root of m. So here, as I mentioned, we will kind of go from 0 to xk minus 1, xk minus 1, since we and from 0 to xk minus 1, because since we will be doing a modulo, we need the elements which are less than xk. These are the elements of our concern. So what here is being done is, for, as I mentioned, for a particular x plus y, from from starting day to this day, which is the from starting day, which is the memo days, from that day to the day of xk. And by mind you, since x plus y is already less than root m, so we can continue the analogy that x is less than root m. So what we are doing is, since from the start day, which from the start day, we kind of go up till start day plus xk days, like plus sk, since like we only care about for how long the thing is in active mode, because after that it will again go to passive mode, and since x plus y, this pattern will keep on repeating, and up till that day we kind of find a modulo. We kind of find a modulo and keep it, and kind of do the same thing as as this part. We kind of either if we have an inclusion, means train is added, we do a +1, and we otherwise we do a -1. Here this kind of being represented as here you can see it is change is either +1 or -1. Similarly, for the next step, it's kind of simple. It kind of starts with the memo day, and kind of the starts keep on incrementing as x of k plus y of k. And here, for but first, as similar to the analogy of the range sum, we add change for the start day, and if start plus xk is less than m, we do a minus in that case. One particular thing to note is this condition. Well, this condition comes in handy when we are removing an element, because if we remember the particular for a particular day, it will have the value of a prefix sum up till the day previous day, and there might be a case in which the element which is getting removed, for instance, like for instance let's consider an example. For instance, the element got started here, and we are now at this index. We are now at this ith index, and we need to get rid of this element. So this simple but if we kind of check here, we're able to see that it will have the prefix sum value from this element to here. Okay, prefix sum value will be here. So when I'm removing this thing, I also need to do a -1 here as well. So as to kind of keep the balance on. So this is that step here, you can see. And then eventually the answer, here the answer represents the number of active elements on the particular day, or like for particular, as I've already mentioned, we kind of get the count of all the elements that we get from case 1. Case 1 is in which the x plus y value of the train is more than root m. But again, we also need to have a count of number of elements which are in active state, which arises from case 2. And for that, we just do a simple for loop in which we kind of find out that for all the elements from 1 to root m, what is the value that we are getting for that day percentage the mod. Okay, that particular day percentage of mod, and finally we are giving out the answer as active minus answer. Okay, thanks for listening. If you have any more doubts or regarding the square root decomposition technique that is being used in the problem, I would suggest you to refer to materials that are available on Geeks for Geeks or other resources to kind of have a better understanding of the square root decomposition technique. Okay, thank you for listening. Goodbye.